sending anything out of your image. Okay. Any more questions?
I don't see more, but and I think also it's time to transition to Sergey. So Jordan, thank you so much. We that was amazing. I'm learning more and more. And please, guys, if you need anything, reach out to Jordan or to me. And also, the recorded will be shared with everyone. And yeah, now we're going to another presentation with Professor Sergei Skakun. This is one of my best presentations because after all what we have been doing this let's say the whole week, I wanted to finish with actually is what we are doing like getting us to where we want, and all these tools, foundational models, sampling data, whatever, does it tell us the reality and does it tell us what we want to address? And so thank you so much, Sergey, for accepting to present in the SIT series. Sergey is an associate professor in the Department of Geographical Sciences, and he is also NASA Harvest researcher. And I mean, I don't know. We come to him basically to tell us what to do for, for everything. So I don't know. Sergey, you can go ahead and,
Yeah,
I mean,
thank you.
yeah.
Thank you, Walid. Let me share my screen. I think I should be able. Perfect. Now you can see my screen, right?
Mhm.
All right. Again, thank you, Walid, for saying nice words, and thank you for inviting. So what I want to touch base in this presentation is about area estimations with emphasis on croplands. So basically in this talk, you will learn about the concept of area estimation. Some of the presentation touch based on that. And I will argue that, of course, things like classification, foundation model that just Jordan was mentioning, it's all important, but there is also important how we infer data and statistics from the maps. Because if we are doing this incorrectly, those maps will be just, and I really like that quote from Rob McRoberts, it will be just pretty pictures, and that's it. Of course, in 30 minutes, I can give as much as possible, and where appropriate, I will give references to foundational paper. Of course, this is not just limited to those, but at least where you can always go and read and get better understanding what's going on. Okay, so let's get started. Yeah, we are compared to what was maybe 20, 30 years ago, it can be called a golden age of Earth observation for agriculture. We have more data, we have more temporal resolution, better spatial resolution, and also we have democratization to a certain degree of computer resources. Now everybody or a lot of people can have just from the browser, can have access to Google Earth Engine, do all the computing and analytics on the cloud and get downloaded data. That is all great things. But of course, it comes at the cost in the sense that the map, and I always tell this to our graduate students, it's great skill to do, I mean, to have to be able to do that, but it's only one of the tools. And we have to use maps properly. And there can be different objectives, of course. And in this talk, I primarily focus on the area estimation. So in terms of Earth observation and satellite data, a lot of our programs work has been done under the umbrella of GeoGLAM. If you're especially talking about global monitoring, and in 2018 they established two systems: agriculture market information system, AMIS, and GeoGLAM. And the reason for that, and you can see that graph chart of the global wheat prices and different anomalies and spikes and some of the reasons for those spikes. and it involves different reasons like winter kill, droughts, so those meteorological events, or oil prices and droughts, and most recently, and let me use my pen, and most recently the war in Ukraine, which spike the price. So the idea was when establishing those systems is to make sure that those spikes not happening, or the amplitude of those will not that too much volatile, and then that we can understand and maybe to mitigate some of those effects. So of course, this is a very difficult problem, and having satellite data, we can have access to basically any parts of the world in different spectrum. Now with the SAR data, cloud cover is less of the problem, still the problem, but less of the problem to a certain degree. So of course, we can then do it on global scale. And we want to do it not only after season, but during season. And this is the work from Christian Abis, PhD student, and now he's postdoc with NASA Harvest, and he had presentation during this week. And I really like this graph, which we call spaghetti, which basically shows how the values of crop production. So this is monthly crop production of wheat in Russia based on USDA reports. So basically how, for example, in June, those reports differ from the final numbers that usually come up around February, March. And we can see that during the in-season, where this is one of the most critical information, because it impacts a lot of decisions, including the prices and contracts, and how much of potential of exports that Russia can do it. We can see that it can go in some years up to 40%. On average, we're talking about between around 15%. And this is the time where the satellite data especially can be efficient, especially given all the constraints on the resources, budget cuts for statistics, etc. So this is the opportunity of satellite data to optimize those. And of course, agricultural statistics is a very broad field, and part of that is crop production. And production, of course, we're interested in two values, in two variables: area, which will be primarily a topic of this talk, and yield. And you had other presentation talking about yield. And another important thing, no matter what the algorithm we're using, no matter what model we're using, etc., in one way or another, we do estimation, right? So we are doing what we call in statistics estimation. And when we do that estimation, we have uncertainties, right? And uncertainties do matter. So because when you communicate that, and you have to be fair with the end user, and you communicate, you have to be fair and talk about uncertainties. And I always say that there is always if you ask a lot of people like what the accuracy of algorithm, there is always magic number of 10%. And if you have 10% of yield and 10% of area, you will have 14% of uncertainty of production. And usually for economy, so if you multiply that 4.5 million tons per around between $200 to $400 per ton, you can calculate. So we're talking about just like that. Uncertainty will account for $1 billion or so. And of course, you cannot just hide or just not account that in the balance sheets in the economic. So because those uncertainties or requirements for uncertainty that might be coming from end user, it will impact our sampling design that we'll be talking later. So now going to the problem of area estimation. Actually, you can do it without satellite data and without Earth observation. The main strengths of Earth observation is we can provide wall-to-wall coverage. So when we talk about wall-to-wall coverage, it means that we map each element of the area of interest, whether it's globe, whether it's country, and we can have information. In other words, we have information on population in statistical terms. Of course, we know that there are errors in the map, and that comes again of the cost. But again, we know our population, and that is not always the case in statistics and sampling. In some areas, we just might not know population. Like, for example, if we did census in some country a long time ago, we don't know the exact population of how many human beings in that country. So you have to estimate that. So when we do area estimation in geographical, of course, subject to the spatial resolution, we know information wall to wall, and we know our population. So what are the some of the uses of satellite data and Earth observation in this regard? And we can provide graphical support. When a lot of us do the ground measurements, it's always nice to have up-to-date satellite data to see what's going on, to optimize routes. That helps a lot. It improves, it can be used for certification, and this is what I'll be talking about a lot in this talk, because certification allows us to make our sampling design more efficient and ultimately to do improvements of our estimates in terms of precision and reducing uncertainties. And it can be also used as a covariate. So it can be used as covariate in many instances. For example, in forestry, it can be used satellite-based derived features. You can relate to biomass, for example, and then you do all the estimations, or you can use proportions, etc. So different like models that you can relate to that. We are primarily in this talk, I'll be talking about mainly about stratification. So this is strengths and pros, but of course, again, it comes at the cost. Nothing is free. So the maps in real world never perfect, right? So, and we will have errors, and we have commission and omission errors. So, and the reason for that is like not perfect data. There is natural confusions between classes. Some classes, we can have enough spectral and temporal features to distinguish them. And some classes, it's still a challenge to do that. For example, it's still challenging to distinguish barley, for example, from wheat or different cereals. Yeah, if you have some local information very nicely, yeah, you can probably do it. But if you're talking about global or even national scale, it's still a big problem. And when having that map with commission omission errors, and if you just take the pixels classified, for example, as the Cropland, and you just calculate that in the number of pixels, this is what we call pixel counting estimator. So this is population-based because we take all the pixels, so all pixels are classified. And you can quickly calculate the area, but the problem with that estimator statistically biased. So depending on our errors, it will consistently be over or underestimating. And in order to know how much, we have to follow some statistical protocol. So why pixel counting? Yeah. So and when we talk about, that's what I started with, is that when we talk about classification, what the data used, what are the features, algorithms, mapping, given the spatial contents, and then area estimation, those, for me, in my opinion, are three separate tasks that need to be addressed, even though, of course, they are related. And but again, as I mentioned in the very beginning, area estimation, actually, you can do it without any mapping, etc. Is that the question how much it will be efficient? And when I talk about efficiency, I'll define that in a couple of slides. So, but just to be sure that we're on the same page, that is why pixel counting is a biased estimator. Just this simple graph like shows that. So let's imagine we have a reference class, which is blue polygon, and then we have mapped class, which is an orange. So we have red one is omission error. So this is what the reference class says. For example, it's Cropland, but our algorithm says it's not Cropland. And then we have commission errors, commission area. So this is where the algorithm says it's Cropland, for example, but in reality, it's not. So you can do all the calculations. For example, reference area will be 144 pixels, mapped area will be 120 pixels, and that will be a relative bias of 17%. So if you have situation like that, your pixel counting will be estimator will be biased. So it means that depending on the omission or commission area, you will have either positive or negative bias. So that's the main problem with bias estimator. There are papers arguing that what are the conditions where you can use it, where you cannot use it. You have to keep in mind that even when you have pretty large values of accuracies, we're talking about, let's say, 90-95%, you can still get, even under that conditions, you can still get biases 10 up to 10%, which, maybe for some applications that's already good enough. Or there are some applications that. So you have to be really careful with pixel counting. And another trivial problem, but sometimes it's overlooked, is which projection you use. So you cannot just take pixel counting like that, for example, when you have latitude geographical projection. So if you have non-equal area projection, you have to account how pixel size is changing if you just count in pixels. So, and you have to make sure that, for example, if you're using Google Earth Engine, that actually it's coming from equal area projections, or it's there is accounting for the, for example, if it's geographical projections, so of course pixel size will be different at different latitudes, so you have to account of that. It's a trivial thing, but sometimes people forget about that, which is a little bit surprising. Okay, hold on. I always. Okay, here we go. So how we then use methods and statistics to actually infer from the maps. In this regard, we're using statistical framework and sampling-based framework. So the analogy is the following. So the same way as if you want to do the poll of the population about some, pressing issues, is we select with a sampling design, we select how we select people, we survey them, and then estimate. So any statistical book, either it's Cochrane 1977 or Sandel 1992, you can read any of those, and this is just classical statistics, how we can do estimates based on the sample. So, and the key here, especially if you're talking about, so there are two approaches, so design-based inference framework, for example. So it's based on the probability sample. So it means that we know probability of including each sample unit, each element of population in there. And it's just this probability and randomization, it does all the trick. I know that sometimes it's just difficult to understand, but it is. Because some people ask, like, okay, you have, let's say, area of United States, and then you select sample size, let's say 1,000 pixels. How, based on just 1,000 pixels, you can estimate the area, for example, of corn or soybean? Actually, you can do that, and the key of that is randomization and knowing the probability of inclusion, and that is where design-based inference framework is included. So in order to, how we use, in this regard, how we use map. We use map for stratification. The map inaccuracy is actually, so it doesn't matter how accurate or inaccurate map. It will not impact the bias of our estimator, because it is depends on sampling design and estimator. So whether your map is 90% producers users accuracy, whether it's 60%, statistically speaking, it will not impact the bias. However, what it's going to impact, so the inaccuracy of the map, it's going to impact efficiency of stratification. So in a couple of slides, I'll be talking about that. And then we can do the model-assisted estimation. An alternative to design-based estimation is model-based inference. So especially it's widely used in forestry, because they're a little bit different perspectives, but it's all part of the statistical framework, how you infer from the map. Ultimately, this is the fundamental problem, how you infer statistically from the map. And I will refer, if somebody interested in model-based inference, for some of those papers, and you can search in RSC or other outlets about that. So some of the key papers, so we have these good practices, Olofsson and RSC. I provide, basically the idea is that you use stratified random sampling with the strata coming from the maps, and I'll show about that. And just recently, literally last month, it was released a new updated version within the Committee on Earth Observation Satellites. So it's CEOS. There are multiple working groups, and there is a group on calibration and validation. And within that working group, there is a subgroup on land product validation with focus on land cover. And there is this report and guidance how you properly do land cover and change map accuracy assessment and area estimation. We don't call it recommended practices, but we call it good practices. And of course, you can read how to appropriately and statistically rigor to do the accuracy assessment and area estimation. So what are the generic steps on that? So first one is sampling design. And again, that in the design-based inference framework, randomization is key. Knowing inclusion probabilities is key. Your sample unit, it can be pixel, it can be polygon, area frame. In this talk, I'll mainly focus on the pixels, even though you can also do area frame. I'll make some comments on that, but here we will be talking about, and then pixels, and then how you do the stratification, etc., etc., etc. So this is all parts of the sampling design. The second step is response design. So basically, you provide definition of what is hit or miss. So what is the match between map and reference? In some cases, it can be just pretty trivial. For example, you classify pixels in the field as Cropland, and you, whether through photo interpretation or through the ground measurements, you say that is Cropland or non-Cropland, and of course, then you classify that. Of course, there are some cases where it's much more difficult. For example, if you have 30-meter pixels from Landsat and you want to do Cropland fraction or forest fraction, it becomes a little bit more difficult, or at least non-trivial. So you have to provide clear agreement on the how you define response design, especially if you're using moderate resolution, like 10 or 30 meter, and your objects like much more smaller in size, let's say field crop canopy or crown. And then analysis, so basically, what are the metrics you use for analyzing your area? And here I just want to mention trivial example. So when you have some area, let's say that occupies 5% of your total population, and you use overall accuracy as a main metric. So if I say there is no such a class there, overall accuracy already will be 95%. So actually providing valid and adequate metrics is also non-trivial, and you have to justify why you use this particular metrics and not the other one. So in terms of sampling design, so it can be simple random sampling. So like this, I'll just put the checkbox. So basically, any unit in your population have some probability. It can be equal. It can be unequal. So there are estimators actually working very well, unbiased estimators with unequal probability. As soon as you know that, it's fine. You can do stratified random sampling. I'll be talking about that in more detail. So when you divide your population into the non-overlapping units, and then you sample each subset separately, and then you can do systematic. That's sometimes very often used in forestry because, especially if you're talking about NFI, there are different sampling designs, and some of those like date back hundreds of years even. You can use unaligned systematic, and you can cluster sampling. So cluster sampling especially efficient when you do ground measurements. So for example, you come to this cluster and then you do local measurements inside. So it might be more cost efficient than you just go through each of these sample units. So you have to clearly specify what's your sampling design. So what's the role of stratification? So basically, certification has two major roles or purposes. So your strata can be the area of interest. For example, your strata can be cropland areas or particular crop, let's say wheat, maize, etc. And the second main purpose of certification is that compared to simple random sampling, it can improve precision of your accurate estimate. So basically, in general, stratified random sampling can provide better, improved precision of your estimate compared to simple random sampling. So in other words, by employing, for example, certification, you can reduce the variance or improve precision 2 times when you use certification. I'll be talking about that in details as well. So, and in terms of analysis, we're using confusion metrics. The main difference is that for a lot of other approaches that we use it in terms of error estimation, and this is critical for error estimation. So each of these, for example, class, for example, P32. So this is our map on the y-axis. So this is y-axis, this is x-axis, our reference. So this is proportion of area mapped as class 3. So because it's like that, but in reality it's class 2. And if we take all of those proportions, of course, it should give us 1. So it means that there is consistency. There is a term consistent estimator. So we need to make sure that in terms of either population or if the sample we have 1. So if you sum up by rows for each column separately, so for example, like this red square, so this will be our actual reference data, proportion of the class reference data. So if you have, sorry, imagine theoretically we have the entire population. So actually it's our true value. So this is our true value that we don't know, of course, because we don't have population metrics, but this is our true value. Whereas if we do it by row, so this is our map. So this is pixel counting, so the green one. So this is our proportion of a class in the map. So this is what the pixel counting. And those, of course, are different. Why they're different? Because all of those elements, P12, P21, all of those elements which correspond either to commission or omission error, they're different. So if we take the main diagonal matrix, it's going to give us overall accuracy. So this is the entire area that's been classified as true, or corresponds to reference, I should say. Then we can do user's accuracy. So we take this, where for particular class, there is correspondence and divide by the entire mapped class. So this is what we call user's accuracy, right? And producer's accuracy, this is what in reference, how much of that reference we can detect correctly. And user's accuracy, it's complementary to commission error, while producer's accuracy to omission error. So on graph, it's going to look something like that. This is our reference class, which will be, in this case, P2, P.2. So this is this class. So this is our reference, true. Again, this is in terms of population. Then we have map class. So this is P.2. So I'm going to go like that. So this is our, and then where they match, or this is our agreement. So this is this value. And then we have omission error. So this is where reference class says, reference area says it's cropland, but our algorithm says otherwise. And we have, of course, commission error area, vice versa. So this is where the map says cropland, but in reality, it's not. So this is some just graphical representation. All right, but what's the problem with this? Of course, we don't know population confusion metrics. because to do that, we will have to provide reference for each pixel of our map. If we can do it, imagine if there is magic, and we can do it manually, then of course, why we need to map it? If you know each, of course, so this is not feasible, this is not, it's like trying to, every time, for example, to ask something, opinion, or to do the poll for the entire population of the United States, which is more than 300 million people. Of course, we cannot do it. So in census, you can do it as much as, and it costs a lot of resources and time, etc. So what's the solution to this? The solution to this is to use sampling techniques. Sampling textbooks from many, many years that's been done, and we do it from sample. So we throw sample and we have the estimate. We don't know the exact value, but we have the estimate based on our sample. Sample is basically subset of our population, and sampling design tell us how we do that sampling. So we know, and that randomization, as I mentioned before, does all the magic because we don't favor, we don't have selection bias. And on that topic, by the way, when computer scientists or someone outside, especially our area, has the following: we have this problem, let's say crop area estimation, and we have some data. Somehow the data were collected, and they claim that, okay, we then have this performance on this data that we don't know exactly how we're collected. And then they claim that they solved that problem. Well, of course, there are several problems with that approach. First of all, we don't know the selection bias of this. And there's also, by the way, there is sometimes terms that bias in data, which statistically it's not real in the sense that, well, you have data, for example, I don't know, like let's say this, you collected fields in all big enterprises, or you collected data on the fields during the road. There is nothing wrong with this data, but what is wrong with the data, there is a selection bias, because it means that there is different probability of including that sample, for example, around the road, and something that is very far from the road, which would have zero probability. So in that selection bias impact the representative of your population. So if you have data that's subject to selection bias, you cannot statistically claim about properties and inference about your population. Just you cannot use the same, or at least you cannot use the same mathematical apparatus as if they were coming from a probability sample. And that is one of the problems. So we estimate area proportion, and this is our estimate. I mean, basically, it's a stratified estimator, which has two components. One is the weight of the stratum, because we have multiple strata. They're not necessarily the same size, so we need to account about that. And then the second term is just estimate of your frequency. So for example, if you have sample size 100 and you take the reference of your sample and it's 70, you said it's Cropland, so the estimate of the frequency will be 70 divided by 100, which is 0.7. So this is the unbiased estimator of proportion or frequency. You can use different terms of that. So this is your estimator of each of the, using those sample counts and the weight of the stratum, which come in from the map for our estimation. So this is all math that I have. I try to minimize it. And then let's talk about concrete specific implementation. So this is what we did in 2022 on the right after the full-scale invasion of Russia to Ukraine. So we produced the map, and then we tried. The objective was to estimate the area early June, July, and see, especially with the focus on the winter crops, because they were planted before the invasion. So we wanted to see what's been survived. So when I talk about throwing sample, and here we use different subdomains. So we throw sample on the unoccupied area, and then the red one is occupied area at that time. So in our case, sample unit was pixel, and we use planet data. It really doesn't matter. So 3 by 3 meters. So all of those green dots, it was our sample that was selected randomly. And we did use stratification. So we had 4 strata: summer crops or potential summer crops, winter cereal, rapeseed, so which is part of the winter crop. So we distinguish winter crops and winter rapeseed and winter cereals, and non-cropland area. By the way, this is one of the actually mistakes that sometimes people do when they do, okay, I have some cropland, and usually cropland class for some countries, it can be pretty accurate. And when I say pretty accurate, it can be 90%, 95%. And people would throw sample on the just cropland and then estimate the area. That is wrong. Because why? Because it doesn't matter what the accuracy of your cropland, if it's 90, let's say 95%. It means that there is a chance that 5% is wrong. So it means that to all your budget, error budget or uncertainty budget, you have to add that 5%, and it will just make it even worse. So you cannot assume that your cropland, so you want to still throw sample in non-cropland area. And this is weights. So I'll just focus on unoccupied. And at that time, because this was like the first one, we just tried with a small sample size to do something feasible. We really obtained a little bit higher variance that we projected. And of course, then we did all the studies in order to optimize that. And now in a more operational way, we know how much sample size we need to reach the desired coefficient of variation. So in our unoccupied area, it was 31% summer crops, winter cereal 13%, rapeseed 2%, and non-cropland 53%. But this is map-based. So this is our pixel counting estimator. So, and then, of course, in ideal world, you want to go in each of these locations or ask somebody and tell me what it is, either it's winter cropland, whether rapeseed, etc. Of course, it's not possible. It was not possible during that year just because of fighting and all uncertainties. And of course, you cannot do it on occupied areas, and you cannot even do it right now. And this is where especially the satellite data becomes even more efficient, right? So, of course, me and a lot of folks in our group, I'm originally from Ukraine, so I did a lot of crop tours back then. So I know what things look like on satellite data. And we basically were photo interpreting as much as we can in cases where it was several of us, and in cases where we're not sure or there were discrepancies. So we sit together and try to reach the consensus. And this is what we got. So this is based on the counts. For example, out of our total number of sample units, so if you just do a calculation for 25, 70 of them were winter cereal as map and were labeled as winter cereal to the best of our knowledge. And then so you do this map. So this is based on the counts, but you cannot use that to area estimation, and you cannot use it for estimating the accuracies, users and producers accuracy, because you have unequal strata. So those total maps, so they were in hectares, and this is your relative weight. So some strata were 27, 24, 16%, 46%, whatever. So now how we do the estimate of area? So we use this formula, right? So the one that I mentioned before. So for example, to estimate the area that the map and reference labels will match, we need to take our weight of stratum 2, which in this case was 0.24. We take the number of sample units that we match, so 70 in this case, and divide by the total sample size in that stratum, which in our case was 100. So if you do these calculations, you will get that the area, proportion of area where the map agreed with the reference for the winter cereals was 17%, 16.8%, or 168. So, and then we do this for each element of this confusion matrix. So, yes, I'll do that. And now we can estimate the areas by stratum and by reference, and calculate and estimate the users and producers accuracy. So first we're gonna do summation by row. So for each column, we're gonna do summation, and this will be our estimate of areas from sample. So this is what we're gonna do for that. And then of course we already have that pixel counted, and it will be 1. And then we can estimate overall accuracy. Well, it's 80%, but in reality, for this kind of study, it was not relevant. 80%, I don't know what it means. Okay, 80%. But in reality, what really important was users and producers accuracy. So 70% for winter cereals of users accuracy. So you take that where there is a match, those 168, and you divide by the what was mapped by the class, by our algorithm, 24%. This will be our user's accuracy. And then you calculate producer's accuracy, which is our from reference. So we would have what it is, 70% or 0.7 user's accuracy for that class, and 87% for. And in terms of area estimation, I usually hate, maybe it's a strong, word, but like people saying like, oh, it's a low accuracy. So it means for me, when I hear things like that, it means that I would assume that that person actually does not know anything, at least about area estimation. Sorry to use that strong language, just because it means that high or low accuracy for what, So you have to keep that in mind, because even with these accuracies, 70% users accuracy and 87, actually it's not so bad. Actually, we can still estimate the areas. So we can propagate that for other classes, and then we can do area estimation. So if we take pixel counting, so that is 24% or 0.24. So in terms of hectares, it will be almost 3 million hectares. But if you estimate from the sample, so that will be not 24%, but in reality from sample, it will be 19%. And you multiply by the total area. So this is our fraction, and this is 12 million. So this was not the total Ukraine, of course. This is, I think it was occupied area, or maybe unoccupied area. Sorry, I forgot. So, but bottom line that we will get 2.4. So the difference will be almost 600,000 hectares. And why it's happening? Because of course we don't have balance between the areas, and actually the relative bias will be 24% between mapped classes 2.9 and or 24% and 19%. And then of course we can calculate the uncertainty. So we calculate the variance, we take square root, we'll get standard error, and then we do the 95% confidence interval. So for example, temporary occupied area. So I recall. So for example, we estimated that there were 2.4 millions of hectares of winter cereals on occupied area and temporary occupied areas of July 2022, plus minus almost 400,000. So what it means, just to be sure that we're on the same page, 95% confidence interval. So it means that if we will be taking different sample, because of course, when you take different samples, so if you randomly will be sample, of course, this area will be changing. Your estimate will be changing constantly because you will be having different sample size. But that is the role of confidence interval to tell you, like, if you throw 100 samples, and don't confuse samples with sampled units, because when I say samples, it means that that is 100 different subsets of population. So in 95%, they will be within this interval, whereas there is a chance that in 5%, our estimates will be actually over this interval. And that is the rule. Of course, if we increase the sample size up to the population, imagine again, this is not feasible, not possible. Of course, this variance or precision will be increasing. So, and that is one of the fundamental problems in statistics. How can we, with the constraints and efficiency, how can we make our estimate more efficient in the sense that how can we reduce the variance of our estimates? And that's where we go to efficiency of stratification. We define efficiency of stratification from two perspectives, of variance and sample size. So let's imagine we have a fixed budget for certain sample size. So when we talk about efficiency of stratification under fixed sample size, it means that more efficient map will provide smaller variance or better precision. So, and that is where the more accurate map that is used for stratification, it will be more efficient because more accurate map under the same sample size, it will give you better precision. And vice versa, if we fix variance and we want to see what the sample size is needed to reach that variance, right? So the more accurate map will give you smaller sample size. What it means that usually it will lead to smaller budget that is needed to label those samples. And it doesn't matter whether you go in the field, you do survey, you do telephone, whatever, or you do photo interpretation from your office. Of course, there are costs associated with that. So more accurate map will be more efficient in this regard, whether improving precision or reducing sample size or somewhere in between. So, and in order to answer that question, so at least for binary case, you can do all the math, and those who are interested, you can look at this paper, and there is also Google Colab and Excel sheets with all the calculations. So when you have proportion, you have a target coefficient of variation, things like that. So you can do all the calculations. I'll just throw quickly this example where you have, for example, a target area is 15%, so it's approximately what the winter crops in Ukraine, and you have target coefficient of variation 5%. So this is what usually our end users want. So if you're gonna do simple random sampling, your sample size will be over 2200. And when you even have very, very inaccurate map, we can all agree that 60% is kind of inaccurate, it still will be 1.5 efficient than the simple random sampling. It means that even under this map, which is like, can be used as a baseline, we can reduce sample size 1.5 times or improve precision 1.5 times. But as we increased our quality of the map, let's say map A, this would require just under 700 sample units. Compared to the simple random sampling, it will be almost 3.3 efficiency. So again, it means that compared to simple random sampling, we would require a 3.3 times smaller sample size, or cost associated with collecting those, labeling those samples. And you can see in between some other values. So, but there is no one solution in the space of PA and UA, users and producers accuracy. So this is isoline, so I'll just do like that, of relative efficiency 2 compared to map of 60/60. So, and this is relative efficiency. So there are multiple. So usually for minor classes like 15% and everything that less than 0.5, we want to have preference a little bit to PA, producer's accuracy. Whereas when you have major classes like 0.6 in this case example, we have more preference to UA. And there is mathematics behind that, but I don't have time to really, because I think I need to wind down, right, Valid?
I mean, you can.
I almost
continue.
done. Yeah.
I think it's
and we can attach that relative efficiency to cost efficiency. And of course, when you talk about relative efficiency, it's relative. So, but if you attach cost efficiency So you can actually attach specific cost associated. For example, in Europe, there is Lucas program, and we can estimate that approximately it takes, depending on the budget, takes one sample unit 35 euro. So if you, for example, have a minor class and you have that accurate map, so for example, compared to simple random sampling, which will cost you in that regard 80,000 euros, 3.3 will reduce budget to 25,000 euros. But if, for example, you have major crop, you will just reduce that just very little. The effect of certification will be little. So that's another thing that, of course, you always thrive to have, better accuracy, more accurate map, better algorithm, etc. But ultimately, you also have to assess how cost efficient it is and what implications of that. Not just say like my map has such and such accuracy and period, but what are the implications, or at least the range of implications of using that map. For example, so I just it's not maybe nearly real numbers because I don't really know how much map generation costs. It's actually not trivial questions regarding, how much computing resources, if you run it on Amazon, for example, web services, etc. But let's imagine we have target 15% fraction and 5% coefficient of variation, and each sample costs $40. Simple random sampling will cost you 90,000. And then, for example, let's say you have pretty accurate map, 90-80%, and with map, the cost will be 52%. And then imagine you try to improve that map 5% each. So you increase from 90 to 95% producer accuracy and from 80 to 85%. And imagine you spend much effort in that and you double cost of that map. So yeah, you improve your efficiency, but you don't improve your cost efficiency, like it will be 73,000. In order to map that to be, actually you can calculate approximately to be cost efficient, the cost of that, improving that to 5% gaze from 90 to 95, from 80 to 85, it should be no more than 10,000 or something like that. Again, this is just, don't cite me on that numbers because, of course, again, I'll just throw that out, that map cost, 30,000. Again, that's actually a nice work to do because we don't really know how much. And it's not to undermine the research, because we have to do research and see what the limits, what we can do. But we have to also keep in mind whether the trade-off and what will be ultimately cost efficiency, especially if we want to implement that in operational context, especially given that the budget are limited, everything constrained, and less costs are being allocated for the statistics. All right, some of the take-home messages. So when maps are used for area estimation using stratified random sampling, map quality will impact stratification efficiency, whether reducing the sample size or improving the precision or something in between. Relative efficiency. So when you report on your class or classes, what is important is not overall accuracy. There are three elements that is important. It's class-specific accuracies, producers' accuracy, users' accuracy, and what are the target class area. This is extremely important because those three elements, they're important to fully reconstruct our confusion matrix. So don't just provide confusion matrix. Because if I just say producers and users accuracy, but you don't provide what the target class area, it's very difficult to know implications of that. Overall accuracy and F-score, at least in the area estimation, usually it doesn't mean anything just because it doesn't impact anything. And you have to justify why specifically you use them. And of course, you have to use rigor map quality assessment, use the Olofsson and COS LPV, and confusion matrix ultimately need to be reported because pixel counting estimator is a biased one. and it's discouraged, and you can get incorrect inference. So yeah, sorry, I took Walid a little bit more time probably than I should have to, but I will be happy if you have time for questions to answer that. Thank you.
Thank you so much. Thank you so much, Sergey. I mean, I have seen this presentation multiple times. I'm reading the paper. I'm coming to your office, and that's always amazing to me how I understand things better every time. So thank you so much. And yeah, don't worry for the time. I think it's probably I mean, thank you for your time to give us and like us answer our questions. We open the floor for the people to ask questions. So whenever guys you want, please share comments in the chat or in the Q&A section. And if you want to talk or ask a live question, also you can raise your hand and I can give you I allow you to talk.
So I'm first, as always. Yeah.
Go
So
ahead, Mon.
Sergey, one of the things we always say in sixth grade is that if someone pays us 50 grand to make a cropped area map, we really can't spend $100,000 validating and giving you a beautiful accurate assessment on that $50,000 map, right? And so, and literally, I think that your numbers are for a nice civilized place. You should try doing it in Yemen or somewhere, you know? So it's really, I think that I'm really happy to be reminded. And what we do is we try to label our accuracy statements correctly. I think that is the biggest take-home message from me, is that there's the proper way of doing it, which we all say, yes, we agree. Then there's the reality, like the way we do it, which is not proper, but if you only have 3,000 points, that's what you're going to use to create the map, not what you're going to use to validate the map, right? So as long as I don't claim an accuracy in an official way,
Yeah.
I mean, what
Yeah,
do
though,
you think
so
that's
like,
a useful?
yeah, I think so. I think it's okay when you have selection bias or for training your algorithm, because we know that isn't, well, it's just not feasible, right? But you have to be, yeah, like you say, you have to be really careful when you infer from that sample that subject to selection bias. You can still do some, estimation, but you have to be careful claiming that it's relevant for the entire population. That's where the little bit of misjudgment can come. Because, for example, if I drive throughout the roads, or I might have fraction of my target class, let's say just 30%, whereas in nation it will be 15%. Or as you know, so if you just sample huge enterprises, your yields, for example, right? Your yields probably will be pretty good, whereas they will be much higher than the smallholder farmers.
Exactly.
And even if the smallholder farmers account for that particular crop, even like, let's say 20% of production, right? So you cannot disregard that, because ultimately your estimate, but I mean, indirectly to a certain degree, those uncertainties of 20%, they will propagate. So, and your uncertainties will be huge. So that is something. Now, in statistics, and I try to kind of look some of the papers, a lot of folks right now is trying to combine what they say big data. So, for example, they're coming from either crowdsourcing or social media, etc., which is subject to selection bias, whether to opinion, etc., with probability sample. And that is still kind of like a question. If you, I mean, you can combine, but ultimately, how much you will improve things. And what I've read, some statisticians argue that you cannot beat probability sample. And that's why I say, like, there is all of this magic in a good way, where you have probability sample, and then you can apply, and there is math behind that, and an applied mathematician, I always like when there is cool math. And when there is like selection bias, and you just cannot use standard kind of estimators. You have to account for that. And that is still, if in audience there are some PhD students, and when I did departmental seminar, I always like, if this is something that, you know, your PhD on your research you want to tackle, there is some, you know, things for improvement.
And I'm sure you're the guy who always holds up their hand, asking the sticky questions, right? But did you get, and then the guy's like, but I didn't do that, you know.
Yeah.
And I think that Olafson paper was really transformative back when it first came out, because
Exactly.
people were doing all sorts of things and reporting papers that for 2008, 2010 really are very squishy, right? And so I think that I'm really glad that we're doing a better job. I'm not so sure that improving accuracy by 5% is worth a huge amount of money. That thing I don't agree with you on, but it does depend on what you're using the data for.
Exactly, right? exactly. Because like, and that is why I always say, like, at least for array estimations, this is what you get. But you might be using maps for different purposes. So, and depending on that, your metrics that you are interested or try to optimize might be different. It's just, you have to be fair in the sense that what you're, because like, you know, again, just reporting overall accuracy and then you improve 2% or whatever is just, you know, I don't know what it means. It's, maybe it means something, I don't know. And again, I don't want to discourage that, you know, like, oh, we don't have to do more research on improving the maps. It's just, my point is that then we have to provide implications what it means. And ultimately, maybe the efforts that you're going to do in operation will be so much, then it will be not worth it for operational array estimation. That just.
Yeah, go ahead, please.
Yeah, I always like when I'm trying to work with like people in the ground, usually they wanna, because sometimes you cannot do statistics like for area estimation locally. Like they cannot do surveys, they don't know how much field they have, they don't know what is like, for example, the real let's say planted field. Or and then we come with and we say, oh, let's use remote sensing, what we are saying. And then like I'm just trying to, like, from your words, what do you think about like people trying to replace, like we'll use only remote sensing instead of like the local statistics, especially at the national level, when people trying to like quantify their like agriculture. Or we have seen like the harvest stat, let's say, idea, which is like more kind of what governments are giving us based on surveys, and then we are coming with remote sensing like to replace. What do you, I mean, what do you think?
Yeah, I think in remote sensing we have several waves of kind of where we were, I mean, as a community, we were promising that everything can be done, and there is then frustration that actually cannot be done. I think the first thing that you have to be fair and say like what is possible and what is not, because, and that's why I say that, Walid, that agricultural statistics, it's very broad.
Yeah.
For example, I mean, like satellite data can help, but I don't know if it's kind of can completely replicate or like substitute. For example, try to do area estimations of all the minor crops in California. It's a nightmare. I'm not saying, you know, or like one time we were asked about Ukrainian statistics, like, can you do potato? Like, I mean, like, or can you distinguish? Yeah, good luck, because those are like in small fields, and I don't know how spectrally and temporally you can distinguish it.
And then there's the yield of potatoes, Sergey, which is sadly underneath the ground and very poorly correlated with the.
Thanks, Molly, mentioning about that, because I didn't even touch the yield, because yield, that's another beast. So about, even if you're gonna do it through cuts or, you know, whatever, and then when you combine those uncertainties from yield, and that is where you have production. So if you and then you have I don't know, like things like what are the practices agriculture farmers are using, and all the kind of questions that you can ask. Sometimes we're not, we can see the physical signal, but we don't know what the land use signal. For example, cover crops, right? You know, we know that in Maryland there are a lot of cover crops, and then sometimes they would terminate, and then they plant something different. But then there is cases when it will be the yield so good, or at least the state so good, that they just, okay, we're gonna leave it and do it from the grain. In no way you would know it from satellite data. And the whole other stuff about grassland and, you know, cattle, livestock, etc., etc. So I think in some areas, in some very maybe small portions, yeah, we can try to replicate and impute and things like that. And there are just broad other things where you can use satellite data as a tool to make it efficient, but I don't think it's gonna ever substitute fully, even for yield, right?
Yeah.
We cannot just impute data fully from satellite data and fully say that it's like it's a truth, right? But satellite data can give you, using different, whether it's VI, something simple, or a little bit more complicated. When you throw sample to do the crop cuts, right, crop yield cuts, or for the field, it can efficiently tell you, like, okay, this is the areas of heterogeneity. So you throw sample, one small sample in this way, in this here, and this here, and then it will be more efficient. So again, but I wouldn't say that you can fully substitute that. I think it's the, you know, like truth is always somewhere in the middle. I think in broader context, it is just will be one of the tools which will provide, will make your decision making process more efficient, but it cannot fully substitute everything. So that will be my response.
Great, thank you so much, Sergey. Yeah, I mean, this is give clarification and language also for us when we are confronting people, telling them like, I mean, we can, but we cannot in the same time. I mean,
yeah, like
we can.
for example, and I know the audience, maybe some of you remember when the Landsat, which is now obviously free and as other. So at some point it was 2000, and maybe even Molly can help me. Then at some point it was $600. And there were studies about cost efficiency, and again, at that time it was just Landsat, so it was 16 days. And at some point it was not cost efficient for area estimation. I mean, it was a little bit efficient. So if it would be free, it would be cost efficient, right? But for that price, it was on the borderline of cost efficiency. Of course, then there is some things like, again, like when you even have historical map and strata, even just cropland intensity, things like that, it can make it efficient. But if it's like you pay fortune of money, it's just will be cost efficient. So yeah,
there are a few questions in the chat.
I think there is one that has to do with the presentation, actually, from Walter. The rest has to do with the recording, and they have already answered.
Yeah.
If you can go at 12:18, Sergey.
Yeah. I think it's more of a comment. Previous research and price analysis showed that if we can identify structural change in supply, can influence in price volatility. Small improvements in forecasting is worth it. Yeah, I mean, like, of course, when you have forecasts, so it's not, I didn't touch base, I mean, on yield, but then if you have forecast of area, at least like how much, what's the state, and then how much will be harvested. Yeah, it's all have effects. So usually, at least for Ukraine, our timeline was that we provide first estimates of winter crops around July, and then summer crops because we need to wait until the signal. And actually, if you want to have information about harvesting, we need to wait in some areas until end of July just to see how much harvested. So yeah, so this is usually timeline. But also the value of satellite data, which is kind of a little bit difficult to quantify, is also like, it's not like ground measurements can always give us all the answers, right? For example, if you imagine, if you do for winter crops, you do early spring survey, and you have some winter crops, but you might not even know if it's like that. You might not even know whether it's, barley, whether it's oats, whether it's wheat, or whether it's even rapeseed. So you have to do several of those tours when it's then later in the season. And then if you want to then quantify how much of that it will be harvested, that's another problem. So at some point you will be like just on tours, and that just becomes very costly. Of course, if you have like a budget of $10 million or something like that, yeah, no problem, probably you can do that. But it's not the case in current world. So you have to do all of these kind of tricks, statistical tricks, and see what you can do from your office just looking at the satellite data, and for what you really have to like go in the field.
The other thing, Sergei, is that I really think that one of the great things satellites do that people struggle with is being truly representative. Because no matter how many times you say you cannot only sample the fields next to the road, everyone always samples because they don't want to get their shoes dirty. They can't access places in the middle of the wherever off roads they don't even know about. Even in the advent of Google Maps, Waleed can tell you how hard it was to get off the road. It's super hard. And and people like, we struggle in sixth grade even to just get agronomists to visit people who are not their friends. They go around to all of their friends and relations because that's what they've always done. We're like, yeah, but you're missing all these other places which need your assistance, that have much worse problems. And even when you tell them, they still go see their friends and relations because people are human, right? And they have huge bias. And I'm always arguing. Just this morning, I had a 2-hour argument with my clients about which data is better, the remote sensing based data or the statistical based data. Like, they're different. They're not, there is better and worse, right? They mean different things.
Yeah, the way that we try to do it within Harvest and with Ukraine, so we have an occupied area where there is some statistics, and we run our approach, and we try to see consensus between. But then there is occupied area where even if we wanted to go, we cannot go. So satellite data is the only photo interpretation. Nobody can go there, right? And yeah, and we try to learn what we can do from sitting photo interpretation. And then there are stuff that we cannot do, and we just, we're just transparent about that. Like, for example, we cannot distinguish wheat from barley. I don't believe anybody who will tell me.
Yeah, we can't do it either. We could do it if we had 100,000 samples of both wheat and barley, which we'll never have. And we have distinct, like the fields are not right on top of each other.
Exactly. In Ukraine, the local feature for that, that on average that work is just something, I don't remember, I think maybe barley, or I forgot which one, but it's like a couple of weeks later planting. And in that particular location,
and the red edge.
And then in the red edge. But locally, if you have the tons of data, like you're Molly saying, you might build something, but it's extremely challenging to do it like for entire Russia or even Ukraine or entire European Union. It's like because that local practices can be absolutely, and then if you have more cereals, it becomes even. We try to do something. Again, maybe you can overfeed for local area where you have tons of good ground truth. Probably yes. But it will not help in regional/national and Yeah, so that's
Totally,
that's a
where
tough
different
thing.
practices are. Yeah,
Yeah.
exactly. Yeah. So I wanted to ask if anyone in the group has other questions that Waleed and Sergey and I can answer on any other subject, like on sixth grade capabilities, or yeah, you know what I
mm,
mean?
yeah.
Yeah.
Meanwhile, I have two other questions for you, Sergey.
Okay.
Oh
Because
my goodness.
I think like because these are questions that I face daily. I answer them in a way, but I think your answer maybe clarify things. So does very high resolution give us better accuracy? See, like people are like usually they invest like, oh, let's not use like Sentinel-2 because 10 meters. If we want to do like potato or whatever, or like even wheat, let's use very high resolution imagery. And I think I want just to know what would be your answer? What do you think about this type of questions?
I think I mean, when we're talking about very high spatial resolution imagery, and if we include planet, right, at 3/5 meter spatial resolution, planet scope, because obviously they have SkySat, which is 50 centimeter. And then if we're talking about Maxar.
Mm-hmm.
So, and those are different because at least in planet, you can get, now they have 8 bands. So you have a little bit better, you have at least yellow, red age, and you have near daily coverage. So you can do some probably cool stuff with that spatial, but then I think you have to justify why you need that in the following sense. Like, if I would always appreciate that at least there will be done some simulation studies showing the effect of spatial resolution. So if your domain is mainly, let's say it's somewhere in Africa or Southeast Asia where you have very small fields, and you cannot see fields or a 10 meter resolution, so yeah, you have to kind of use it, or you will do some data fusion. The problem with the LED sub-meter resolution data, you will never have a good temporal coverage. You might have one image, it's just there is no capability there. So if you're talking about very high spatial resolution, less than 1 meter, you won't be able to produce reasonable map. If you're talking about crop type map, maybe you can get cropland in certain regions. But we know that in some regions, you really have to have. So I think like the next approach is kind of like when many years ago we have Landsat and daily MODIS, and you do data fusion. So now you kind of go one hierarchy less. So when you have non-regular sub-meter data, but more regular like planet data, but you have to justify why you want to do that and efficiency of that. Of course, if you're talking about like very, very precise field boundaries, yeah, that's, or you're going to do cadastre and just try to do the, basically, you want to have the entire population of fields or parcels. That is where, even in countries with large field size, you probably want to have high-res data. Just what you say, you were saying, Walid, that like just knowing how much cultivated area, what are fields are there, or potential fields are there. So I don't think one size fits all, and then you can always run the cost efficiency analysis and calculate how much it's going to cost you if you want to try to cover 50 centimeter the entire country with SkySat and Maxar imagery. It's going to cost you probably millions and millions of dollars. So, and I mean, I would be surprised.
And that's only for buying the data. That isn't for the processing.
Oh yeah, exactly.
storage,
Yeah, and then you have, yeah, exactly. And then you have to have people that know how to deal with all of these and have storage and do
Same goes for
preprocessing.
drones. Drone data is, you can have great temporal coverage, but who's going to pay for the mountain of data you have to wade through and store?
That the same, yeah.
Centimeter scale, it's horrible. We've never been, we can show the picture, but only once. I can't do more than one.
Yeah, so those, for example, can be used as the like sample labeling tool, or like drones or high res. I know that they use it, for example, for forestry and global, the way you kind of use better spatial resolution compared to Sentinel or Landsat. and then you try to label that. So I know that it's kind of certain degree answers and then non-answers your question, just because it's not like black and white, unfortunately. For example, for Ukraine, just to give you usually Ukraine, obviously we have big field sites, right? So usually it's enough to have 10 meters. But then if you want to have a population of smallholder farms and you have the field boundaries for that, you really have to have some high-res data in certain regions. So you want to do a mixture. You want to sample or at least acquire high spatial resolution data in those regions where you really need that. Whereas for the majority, you will be probably fine with the 10-meter Sentinel data. So and then you have a mixture and a little bit of cost efficiency of that.
Yeah. Well, thank you so much, Sergey. Yeah, I think that was my my goal is to basically have your saying about this type of like questions, and because I mean, I say the same thing every time, everywhere, but then it's just very complicated to convince that remote sensing will not solve everything, and like like having a better model, let's say the most, let's say deep learning, whatever, will not solve everything, and also very high resolution will not solve your goal when you don't know your goal or when it's not doesn't fit the goal. You know what I mean?
I think also, Walid, sometimes there is a little bit like a wrong way in terms of road. And I understand when you want to do proof of concept technology, etc., that's all fine, you do it.
Yeah.
But then you have to ask yourself, not like, how am I going to use the tool? You should ask like, what the problem and what will be appropriate set of tools, rather than, oh, we have this and we have to solve this problem. But maybe that is the wrong solution, or maybe it's not the only solution, things like that. Like I always joke, like in math, when you have a problem, the first thing you need to know whether there is solution to that problem. When there are multiple solutions, well, and then if it converges, like, in numerical way, like, because you can have perfect theoretical solutions, but you cannot do it numerically. So I think sometimes you should ask those questions in real life, like, is there a solution? And if there is, what are the solutions? And what are the most efficient solution if there are multiple solutions? And not about the around, oh, we have this, and now we have to solve the problem with this. Whereas we don't know, maybe that is appropriate or maybe it's not,
Yeah. Well, thank you so much. Thank you so much, Sergey. That was very insightful. Molly, I give you back the
Well, I just wanted to say thank you to everyone for attending and for engaging with us. Please send Walid an email if you'd like more information. And just use our URL. I'm sure he's going to send a follow-up, right?
Yeah, the goal of this form basically is to have all your emails and interest in the upcoming session and the recording. So thank you everyone for all these amazing 4 days. We had a great time, and yeah, hope we will meet again. And thank you for all who stayed with us until the end.
Yes, thank you so much. I can tell you I'll be scrutinizing that Jordan proposal presentation since I didn't understand half of it. So yeah, exactly. Okay, thank you all so much. Have a wonderful weekend.
Thank you. Bye.